This is Dr. Hal Needham with a brief presentation called USurge Data Sources. So storm surge is one of the world's most catastrophic natural disasters. Actually, here's a picture of my neighborhood taken 117 years ago during the 1900 Galveston hurricane. This was a Category 4 hurricane that produced a storm surge around 16 feet, or around 4.8 meters, that just slammed into Galveston Island by surprise and destroyed much of the city, killing over 6,000 people in the most deadly natural disaster in U.S. history. I was interested to study storm surge from a climatological perspective when I started grad school. So basically looking at large data sets and analyzing them to see what is the frequency of an event like this? How often do they happen? And what is the magnitude? How big can they get? When I started grad school in 2008, I was surprised to see that there was no comprehensive storm surge database. This really confused me because as someone with an interest in climatology, I found that there were climate data sets for all kinds of different data. For example, snow, drought, temperature, and rainfall. We have extensive data sets and maps for these data going back a long time, many decades. But for storm surge, there was no comprehensive data set, and I didn't really understand why. I started looking through the tide gauge record to get an idea of why we don't have a comprehensive data set, and I found, for example, NOAA Tides and Currents has a network of really dozens of tide gauges in Hawaii, Alaska, the Pacific coast, the Gulf Coast, and the Atlantic coast. And these tide gauges will every 6 minutes measure water height. So they will provide these graphs where the blue curve here shows predicted astronomical tide levels, and the green line here are the actual water levels. So in a case where we have persistent onshore winds, often the green level will be slightly higher than the blue. So in this case here in Apalachicola, we see that that the actual water levels are slightly higher than predicted. So this works very well. Typically, these gauges measure tide levels every 6 minutes. However, during a storm surge event, things change. So, for example, I looked at data from Hurricane Ike in 2008. This is a map of Hurricane Ike's position early in the morning of September 13th, 2008. The red area here is experiencing hurricane force winds. The orange area here is a polygon showing tropical storm force winds. If we look at the periphery of these winds, for example, out here by Shell Beach, just southeast of New Orleans, we can see actually, again, one of these graphs where we see blue are predicted tide levels, the green are actual water levels, and we can see here for about 2 or 3 days the water level is much above normal, or much above predicted. And this is Ike's storm surge coming in. And the water levels here reach about 6.5 feet above mean sea level, but they would be predicted to be about 1 foot above mean sea level if there wasn't a hurricane. So the difference between actual water level and predicted is the storm surge, which in this case was about 5.5 feet high. So this tide gauge here really accurately measures every 6 minutes the water levels, and we can really see the progress here of Hurricane Ike's storm surge. However, when we move closer into the heart of the hurricane, towards near where it made landfall, for example, over by Galveston Island, we also have a tide gauge there from NOAA Tides and Currents. The blue line are predicted water levels. The green line here are the actual water levels. So water levels are increasing. When they get up to around 10 feet or 3 meters, the gauge actually malfunctions for a period of time. So we as the audience don't know if that water level flattened out around 10.5 feet, or did it spike up here around maybe 16 feet or 4.8 meters. We don't really know. Sometimes storm surge events will really spike. Sometimes they'll flatten out. We don't know because the gauge malfunctioned. The gauge was not washed away or destroyed because we're picking up data on the back end. So it appears that this gauge could not measure water levels once they got above maybe around 10 feet or about 3 meters. And that's a problem because, again, they faithfully measure water levels when there isn't a major hurricane, but when we have a large storm surge, often these permanent tide gauges will malfunction. As a solution to this, USGS actually they created this program where they have mobile storm tide sensors that they'll put out before a hurricane makes landfall. So these data are from Hurricane Matthew in 2016. And this is a great solution where they'll get out there and they'll put really dozens of mobile storm tide sensors to measure water levels. These data are available since Hurricane Rita in 2005. So, and they're very accurate, precise data. USGS will create reports where we can go back and get these numbers, or even on this website we can see exactly what the water levels were. But for going back before 2005, it's difficult sometimes to get all of the data through tide gauges. So long term, though, tide gauges are great for peripheral storm surges. So again, Shell Beach there, we were 250 miles from the landfall of Hurricane Ike. We could get an idea when that storm tide was around 6 feet or 5 feet. Also, tide gauges are great for long-term sea level rise analysis. So this is a graph of tide levels, or basically sea level, in Annapolis, Maryland from 1928 to present, and we can see there really is a long-term sea level rise trend. And so long-term tide gauges are great for looking at this idea of nuisance flooding, or sometimes we'll hear of sunny day flooding in places like Annapolis and Norfolk and Miami, where actually the impacts of sea level rise are already being felt in these locations. Long-term tide gauges do a great job with this, but again, with large hurricane storm surge, sometimes they struggle. So when I was looking through data, I found that the tide gauge sensors were helpful, but we also needed data from other sources as well. A second source that I found that's very useful are storm reports. So, for example, FEMA and USGS, U.S. Army Corps, there are storm reports. Some of the best reports are available through NOAA's National Hurricane Center. So going back to 1958, we'll see these reports for different hurricanes and tropical storms that struck the coast. And in the back of these reports, there are often tables that provide storm surge and storm tide levels that we can pull out and put into a database. Another source that I found was particularly interesting are historical maps. So the U.S. Army Corps has a lot of these great historical maps going back to the late 1800s. This map is for sometimes what we call the forgotten hurricane of 1915, because a lot of people have forgotten about this or don't even know this actually happened. This was a major hurricane that struck southeast Louisiana, making landfall here west of Grand Isle, and then the storm tracked up through the western suburbs of New Orleans and across Lake Pontchartrain. So what's interesting about this map, a couple things. For one, it's produced from data from 1915. So sometimes we think back more than 100 years ago, we might think, these people didn't have internet, they didn't have smartphones, but they did have pencils and pens, they had paper, and they had rulers and tape measures, and they could go out and actually measure these water levels and record them, and they did. Actually, you can see here everything shaded in gray was flooded by salt water, so this was the extent of the storm surge here. And all these little numbers here provide a dense network of observations, and that's really interesting and useful, because storm surge is a very localized phenomenon. What I mean by that, sometimes if we just move a couple miles in one direction or another, we can see drastic changes in water levels. Look, for example, here along Lake Pontchartrain. Right by New Orleans on Lake Pontchartrain, the water levels here range from about 4 to about 6.2 feet. Up here in the North Shore, up by Mandeville, for example, water levels range from about 6 to about 7.7 feet. But look over here on the western end of Lake Pontchartrain, over by the little village of Frenier, water levels reached 13 feet. That is not a mistake. That's actually very accurate. A similar thing happened during Hurricane Betsy in 1965. Betsy tracked more from southeast to northwest, but we also had water levels of 13.1 feet in this area. So we've had that twice, really, in the last 102 years or so, these water levels reaching about 13 feet. Why does that happen? When a hurricane is positioned south of New Orleans, incredibly strong winds from east to west will push storm surge into Lake Pontchartrain and really pile it up here on the western end. And these water levels will be more than twice as high as what's happening over here in New Orleans or up here by Mandeville. So water levels can tend to be very localized, and sometimes our network of long-term tide gauges is not dense enough to actually record these localized changes. So historical maps and people going out and measuring high water marks can really get a much more dense network that can be recorded and help us to see these patterns. Historical photos provide another data source. So, it said a picture's worth 1,000 words, and it's really true. When we look here, for example, at this storm surge event that struck Miami in 1926, we can look at this photo and see some landmarks, for example, like these telephone poles. Here's a transformer box, so if we knew the height of this, we can look back and get a pretty good estimate of what this water level was. This is useful for a couple reasons. For one, it really gives us a good idea of what the water levels were. It also helps with education and outreach, right? So we talk a lot about sea level rise in the Miami area. Sometimes we don't hear as much about storm surge, though, because Miami hasn't really been struck by a storm surge in a long time. In fact, it's been 25 years since Hurricane Andrew, since water level has reached within 7 feet of this level from 1926. So this picture you're seeing here is from the highest recorded water level in the history of Miami, where a storm tide came in about 15 feet high. Water levels have not reached within 7 feet of this level in at least 25 years. So this really can give people a good idea of, wow, this picture shows that this happened before and it will happen again. High water marks are very useful. So FEMA, for example, sends out teams of scientists that will measure high water marks after large hurricanes, especially since Hurricane Katrina in 2005. The city in which I live, Galveston, Texas, we might have more high water marks than anywhere I've ever seen. We have high water marks all over the city. For example, near Mod Cafe on Post Office Street, we have this high water mark here from Hurricane Ike. It says September 13th, 2008. We also have a plaque here saying that this building was a 1900 storm survivor. So several thousand buildings did survive the 1900 storm, and we have markers on those throughout the city to show you which buildings survived the storm. So going back through time, we can use high water marks also to recreate what happened. And then a final source are newspaper archives. So during my master's degree, I read daily periodicals, actually 16 different newspapers from around the Gulf from 1880 onward. And these data were particularly important for the early part of the record and also for lower magnitude storm surge events. So, for example, if a 5-foot storm surge hit 100 years ago, it might not have made it to some of these maps or, gauge records, but it might be in a newspaper. So, for example, the Times-Picayune from New Orleans. We have newspaper clippings here from 1931 and 1943. The 1931 article says, accompanied by driving rain, the gale kicked up a 6-foot tide that pounded the seawall and dashed over the coastline highway. This is talking about a storm surge event that hit coastal Mississippi in 1931, and it says a 6-foot tide. The term storm surge is never used in the literature before until after 1960. So pre-1960, literature will just say tides. They'll say a 6-foot tide, or the tide was 5 feet above normal. It implies that this is a water level above normal. It's essentially a storm surge height. And it talks here about the tide that pounded the seawall. So we get the idea here that there may have been wave action involved. And typically storm surge and storm tide data, we want to remove the waves. So these anecdotal sources, we're not getting a extremely precise idea of if waves were included or not, or things like that. So we have a little bit lower confidence in their accuracy, but nonetheless, we know that something happened. We know that there was about a tide about 6 feet above normal. We know it wasn't 10 feet. We know it wasn't 2 feet. We get somewhat of an idea, and it's better than having nothing. This article here from 1943 in the Times-Picayune talks about a tropical storm that struck Texas. It says residents flee as a 60-mile-an-hour wind heralds storm. A majority of the residents of Freeport departed as a 60-mile-an-hour wind struck there late Thursday night, a dispatch stated. The barometer reading was 29.84 and the tide 4.5. So again, the tide 4.5 feet above normal. We have a pretty good idea of what the water level there was through a newspaper clipping from 1943. So as we assembled these data, and as I did a lot of this work for my master's degree, we were able to publish some papers that I worked with some colleagues on. There was a paper published in 2012, a paper in 2013, and a peer-reviewed paper also. These are all peer-reviewed, another paper in 2015. So quickly to walk you through these papers, and the reason that it's important to publish on these types of things is to show scientific credibility and that the academic community agrees that this is scientifically sound. The paper in 2012 that I published with Dr. Barry Keim from LSU is called A Storm Surge Database for the U.S. Gulf Coast. It was published in the International Journal of Climatology. Really, in this paper, we created the first snapshot of storm surge history along the Gulf Coast from 1880 to present. And we, for example, mapped out the location and height of peak storm surge levels. And so every circle on this map is a unique storm surge event. The larger, darker circles are higher magnitude storm surges. And so anything over 13 feet or 4 meters is in red. Anything in purple is over 5 meters or about 16.5 feet. And we see a lot of red and purple circles here along the northern and western Gulf Coast, also in extreme South Florida and the Florida Keys. But look, for example, along the west coast of Florida, from around Naples and Fort Myers up through Tampa and around through Apalachicola, we don't see any of these red or purple circles. And so that means since 1880, we have not observed any storm surges in those areas that have equaled or exceeded 13 feet. It doesn't mean it cannot happen, though. And so, for example, if we had a hurricane tracking from southwest to northeast, which is not as common of a track, but it can happen. And if you look back in the paleo records, we see that there's evidence that these storm surges have happened before. But for example, models suggest if we had a hurricane moving from southwest to northeast, making landfall north of Tampa, we could see a storm surge of 6 meters or 20 feet in the Tampa Bay area. So again, we haven't seen that since 1880, but it doesn't mean that it cannot happen. So one of the limitations of this study was that every storm surge event is signified by a circle on this map. So for example, Hurricane Ike is this purple circle here in coastal Texas. However, Ike actually flooded the entire Gulf Coast from Texas to Florida. And so to improve upon this, in 2013, we published a paper that actually broke out these storm surges. Instead of one observation per storm, it provided all of the observations for all of the storms. This article was in EOS Transactions of the American Geophysical Union, and it was called A Global Database of Tropical Storm Surges. In this data set, we talked about expanding the data set globally, also separating out storm surge and storm tide, and making references to datum or vertical reference marks. So focused in a little more here, zoomed in on Hurricane Ike storm tide. Again, the highest water levels were in here, Chambers County, Texas, around 5.3 meters or 17.5 feet. But as we make a more of a spatially accurate depiction of high water marks, we can see here, for example, south of New Orleans, water levels reached 8 to 12 feet. And that really is something we're moving, 250 miles east of the storm track, and we can see really substantial storm surge here south of New Orleans. As we did this as well, we could build these data sets into a GIS or Geographic Information System for analysis. The final paper on the real credibility and establishment of this database was in Reviews of Geophysics in 2015, a review of tropical cyclone-generated storm surges, global data sources, observations, and impacts. And really in this work, we looked at what I had done in my PhD to develop the first comprehensive data sets for places like Australia, the Philippines, China, India, and Bangladesh, really going global with these data sets, and also talking about the impacts around the world. So bringing these all together in my grad studies, we had created a data set that we called SurgeDat. So this was tropical cyclone-generated storm surges from 1880 to 2014. So 135 years of data. And this provided over 8,500 high water marks for the U.S. And this is coming from about 350 unique storms for the U.S. and about 350 internationally as well. I left academia at the end of 2015. As I left grad school and wanted to branch out on my own, I thought of some ways that this could be improved. And the biggest way I thought of is that we can have thousands and thousands of high water marks, but what people really want to know is, what about in my backyard? What about in my community? What's the comprehensive data set and the statistical analysis? And so when I branched out on my own, I started a project called USurge, and USurge focuses on localized data and analysis. So we're really looking at your community. The time period is 1880 to present, so it's presently maintained. And I work on this data set almost every day, and I've realized the importance of just keeping this really maintained and up to date as well. I've added about 500 or 600 additional storm surge observations and made a lot of corrections of errors that were found in SurgeDat to really keep this as accurate as possible. So now there are over 9,000 high water marks for the U.S. And I've also improved the datum conversion. So USurge uses improved conversion methods where we can bring everything into the same datum reference, which is important. When we say a water level was 4 feet, we need to know 4 feet above what and have consistent datum conversions. So where does USurge get its data? That's the question I'm asked the most. And actually, we get data from everywhere. So USurge gets data from tide gauges, from storm reports, historical maps, historical photos, high water marks, and newspapers going back until the late 1800s. Thanks again for tuning in. Again, my name is Dr. Hal Needham. Shoot me an email at hal@marineweatherandclimate.com or visit our website at www.usurge.net. Thanks so much for your attention, and make sure you check out the other videos. We'll talk about why doing data-driven storm surge analysis is important, and also some tools provided by the USurge project. Well, thanks again for your attention, and I hope you have a great day.